Okay, here we are with PowerPoint 3.2.6 about beam design. And this PowerPoint is going to cover some basics about the elements used when we're figuring out what beam we need to use. These are the different topics we're going to cover in the PowerPoint. And first we're going to start with beam design, and we've seen this exact same diagram in another PowerPoint where we're seeing bending. It's bending down, and how far it bends down is called deflection. We didn't calculate that in the last activity, but we are going to be looking at that now. And we do want our beams to be minimum sized so that we use the minimum material. How deep the beam is, how tall the beam is, will cause our project to be more expensive. So we want to use the minimum size we can while still being safe. We've been looking through this steps in beam design. We did 3.2.2 on loads, and then we analyzed the beams in the last two sections. Now we're going to be doing these next three steps. There are some important ideas which we went over in Principles of Engineering, but we'll quickly go over again here. Stress is an important concept. The stress is actually the force divided by the cross-sectional area. If we just looked at how much force went on things, then it wouldn't be proportional based on different sizes of areas. When we divide the force divided by the area, we get stress. And stress is represented by a lowercase sigma. This little symbol right here is always stress, and it's always force divided by area. Axial stress is when I'm pulling on both ends straight along the axis of the member, and the stress is what's felt inside by the material. Here's an example problem. It's just plugging in the force and the area. K is kips. A kip is 1,000 pounds. Strain is the other one that's important to us. Strain is always represented by an epsilon, and it's always delta L over L. Well, we should know that delta means change in, so this is the change in the length, how much longer this got when it was pulled on, and then L at the bottom is the length of the original member. So here's a small example of this, plugging in. We did have to convert the length of 16 feet back into inches, so these units are the same. And you'll notice this does not have any units. Strain does not have any units. I've given you a copy of this stress-strain curve to put in your notebook. Please make note, this is the ultimate stress. This is the absolute most stress that you can get on an item. This is the yield stress. And this section is linear, and it has a slope here, and the slope, the rise over run, is actually a capital E, which stands for the modulus of elasticity. We have this for most materials that we use. There's two parts to this curve. There's basically this part on this side of the line here where it's a linear portion of the graph, and that's the elastic behavior side of the graph. Label this on your diagram you're putting in your notes. And in this section, I can pull on the material and it'll still return back to its same shape and strength. Think about a rubber band in this section. In the elastic section, it's like a rubber band. You pull on it, you let go, it goes right back to its natural shape. From here forward, if I've stressed it to the point that it goes past the yield point, label that on your picture, if it goes past the yield point to this section, it will never return to its original shape and strength. This is a place, think of like a plastic water bottle. Once you've bent it, it's never going to go back to its original shape. And what happens is we hit the maximum yield here, and then you can keep adding more strain to it and pulling on it, and eventually it fractures. Add this point to your graph. We want to keep all our designs where all our designs stay in this linear region. That way when we apply loads and take them off, our members still maintain the same amount of strength they had originally. Factors of safety are extremely important in civil engineering. A factor of safety is a ratio of the maximum load to the allowable load that our code tells us we can use. And every part that we design in a building has a factor of safety. because we're very concerned that we don't want our buildings to fall down. ASD is an abbreviation you're going to see. It stands for Allowable Strength Design, and this is the design that comes from code that tells us what factors of safety we have to use. These are the factors for straight forces in our item, forces as compared to moments. Our factor of safety here needs to be less than the nominal strength divided by the allowable strength. Bending. Bending, here we have moments, so that's bending. Notice that the factor of safety, it is represented by an omega, and we put B for bending. It's 1.67, and again, we can find it by doing this equation and this one, you'll notice, are just rearranged algebraically, and we use these. To find the nominal bending strength, this may look like a new formula, but remember, moment equals force times distance. So it's the same thing, but we're just using some different ideas here. This is the nominal bending strength that we saw on the last slide. This is the yield stress, which remember is just force divided by area, and the plastic section modulus. You will be using this web page and this activity to look up this table and pick the correct beams that we're going to be using in our design. Most of our beams are I-beams, called I-beams because of the shape here. These ends of the beams are called flanges, and the inside is called the web. This is the thickness of the web right here, and the depth actually goes from the top to the bottom. You'll notice that they put axis, like a coordinate system, where this is the x-axis, and this is the y-axis, and this is the x-axis. It's a W is the designation because it's a wide flange, and W12 by 58 tells us information. Here we have the allowable shear strength. Again, shear is where one part is sliding against the other. And we can see the nominal shear strength is the 0.6 times the yield stress of steel and the area of the web. And we can get these information from our table over here. Beam deflection. Remember, this is how far the beam bends when a load is applied. And these are the limits that we can allow to do it. Now, why do we have different limits for a plaster ceiling versus a non-plaster ceiling? Well, it's really just aesthetics. Ceiling cracks in plaster. If it's a plaster ceiling, it's going to crack, so we're going to have so we want less deflection when we're dealing with plaster. These are going to be the steps we're going to use when we start our activity. And this is going to be the end of our video over the PowerPoint.